All right, so this will be a little bit long. This covers basically all the information that you'll need to know for your quiz. Your quiz is basically a unit test. This will be your assessment for this part of Earth science, um, and we're going to go over it all. So before, if you'd like to watch any of these YouTube videos, they are available to be viewed. You'll just have to copy the link and put it into your browser, and you'll be able to find it. So most people used to think that the Earth was flat, but because of that, now we know better. The Earth is actually a sphere. So the sphere is so no matter where you are on Earth, objects fall straight towards the surface as if they're falling towards the center of a sphere. So the Earth in Earth's center is going to show you. Because of that, we see that the Earth has a gravitational pull. It's not because we're on a flat surface and it just falls off there. The Earth's shadow, another way to prove that the Earth is a sphere is the Earth's shadow on the moon during a lunar eclipse. So based on that, we see that there is a curved shadow. Uh, Also, if you throw an object, it will always, over a long distance, curve because it curves around towards the surface of the Earth. So it is falling towards the center of the Earth. So ancient observers in different parts of the world could see different stars. This means the Earth is not flat. If you see different stars, that means you're not seeing, if everybody would see the same stars if it's flat. By seeing different stars, you're seeing that we have different areas of the Earth that are rotating differently. So thus we have a rotation of the Earth. There's several different ways to find it. So the gravity is an attractive force between two objects, depends on the masses of each other. So because of gravity, we know that the Earth's shape is not flat. And like I said, watch these videos and they'll prove to you. So Earth's magnetic field is based on the rotation of the core. So if we have no rotation in the core, we don't have a magnetic field. The mantle, as it rotates around the core, creates this magnetic field. So the Earth's magnetic poles will move towards each other, creating a magnetic field around the Earth. So this, when the axis is tilted about 11.7 degrees from Earth's geographical axis of rotation. So the magnetic field protects us from solar wind, protects us from the harmful radiation of the sun. The atmosphere protects us from objects and part of the radiation, but the magnetic sphere makes it possible for us to not get all of the excess radiation from the sun. Being closer to the poles actually gives you more radiation than being further away. So the locations of the magnetic poles will change slowly over time. So eventually, magnetic reversals occur about every 200,000 years. So at about 200,000 years, it will switch. So the North Pole becomes the South, and the South Pole becomes the North. And it's just the way that the magnetic poles work, not necessarily the position of the Earth. The Earth won't necessarily flip on its head, but the magnetic sphere will. Auroras. So you've heard of the aurora borealis, where you can see it in the north. It's all of the sun's radiation bouncing off the magnetic field of the Earth. It produces these electrically charged particles. So your electrons start to get excited and create new colors that you'll see. On some years, you can see it all the way down into the northern states in the United States, and not just in Canada and Alaska. So these lights are called the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. So you'll see it in both. So planet Earth has an orbit shaped like an ellipse. So an ellipse is more of a oval than it is a circle. So there is no perfect diameter around the sun. So Earth is closest to the sun in early January and further away from the sun in early July. So that doesn't make any sense to us, does it? So summer's in July and January is winter. So why would it be colder when we're closer and warmer when we're further away? Well, that has to do with the tilt. So Earth is the only planet whose characteristics makes it possible for life. Based on the atmosphere and based on the magnetosphere, it protects us and gives us the needed particles for survival. So the Babylonians devised a way to come up with time. So think about the way the sun hits us. So because their counting methods, they based on 60. So they divided the circles into 360 parts. So that's why there are 360 degrees to a circle, based on the Babylonians. So if there's 360 degrees to a circle, there's 360 degrees for a sphere. The symbol is a degree sign taken from the symbol for the sun. So as the Earth spins, it takes around 24 hours each day. This spinning causes the sun to appear to move across the sky from east to west. Even though the sun is still not moving, the Earth is spinning, giving us that manipulation of, or the assumption of the sun moving. If the Earth spins 360 degrees in 24 hours, then it roughly spins about 15 degrees in 1 hour. That means a time zone is 15 degrees. So for convenience, time zones are modified to fit around a city, state, or county borders, debate based on where you're at in the country or in the world. So you may actually be in a different time zone, but it makes it easier for you if they move it. So the international dateline, this is in the Pacific. So one is drawn there, directly opposite of the prime meridian. It is the starting point of a new worldwide system of measurement. So time is based on the UTC, or the Coordinated Universal Time. So once you pass that international dateline, you're in the next day. So the only way for you to time travel that we know of is you can fly from Tokyo to Los Angeles on the 5th of July, and when you get to Los Angeles, it'll be the 4th of July still. Pretty interesting, right? It's the only way to go back in time. So rotation is the spinning of the Earth on its axis. A revolution is one time around the sun. So rotation on the axis, 1 day. One rotation is 1 day. A revolution is one time around the sun. So one orbit. That's a year. So revolution is measured in years. Ecliptic is defined as the plane of the Earth's orbit around the sun, because it's an ellipse. Why do the seasons change? Well, that has to do with the sun's tilt, the Earth's tilt, the location of the sun. So the number of hours of each daylight, the angle at which the sunlight strikes the Earth, and the various Earth surfaces. Remember, the Earth's axis is tilted around 23.5 degrees. So you can see when you are in September, it's autumn here, spring in the southern hemisphere, and it will always be opposite based on where you are in the world. So if it's spring in the northern hemisphere, it's fall in the southern hemisphere. So the hemisphere tilted closest to the sun will receive more sunlight at higher angles than the hemisphere tilted away. So that's why when we're tilted towards it in the summer, we get more sunlight, so it's warmer, and the southern hemisphere gets less. So the greater intensity of sunlight is one reason why summer is warmer than winter, but it's not the only reason. So as the year progresses, the number of hours of daylight in each becomes fewer. It reaches a minimum on December 21st in the northern hemisphere, which means it's a maximum on the southern hemisphere. So solstice, the hemisphere of the earth that is tilted towards the sun, receives more daylight than tilted away. So a solstice is the point at which the sun reaches the greatest distance from north and south. So winter solstice, summer solstice. Now equinox is different. Equinox is when they receive exactly the same. So our equinoxes are March 20th and September 22nd based on our dates. That's when we'll see an equal amount of sun and nighttime hours. So 12 and 12. So remember, a rotation, it takes 23, so this is different. So rotation is one time on its axis, and revolution is one time around the object it is orbiting. So it takes around 27.3 days, so almost 28 days for a moon to revolve around the Earth. Because the Earth also revolves around the sun, it takes more than 2 days for the moon to line up with the Earth and sun. So basically 30 days to line up with the Earth and sun. So we call this lunar cycle. Basically, it is a synodic month or synodic month. So 29.5 days to see a complete cycle of the moon. You'll see a new moon or a full moon once every 28 days or so. So this is called the synchronous rotation. So the moon affects Earth based on how it revolves around it. So this revolution and the distance away, it has enough gravity to produce rise and falls of the tide. Now, it is not the only one that does the rise and fall of tide, the sun. So basically, they're doing a tug of war with our ocean, creating this rise and fall of the ocean. So high tide is when it gets to sea level, and about 6 hours later, as a trough of the wave approaches, sea level drops, causing low tide. So the sun is further away from the Earth than the moon, and this is why the moon has a greater effect on tides. So as the moon drifts away from us at about 2 inches a year or so, or 2 centimeters a year, I believe, it will gradually get far enough away to where it won't affect our tides as much. So the Earth's tides are an example of how the sun and moon operate in a unique system. So when the sun and moon are aligned, they pull together with greater force, producing stronger tides. So spring tides are your stronger tides. Your neap tides are your weaker ones. So when we have our full moon and our new moon, those are our spring tides. And our neap tides are going to be when we see our quarter moons. So when I mean quarter moons, we're talking about our different phases. So moon phases reflect the amount of surface that we can see based on where it is in location to the Earth and Sun. So of course, our lunar cycle is 28 days relatively. You see that a complete cycle with the sun is going to be 29 days. So we're looking at anything between 27 and 29 days. So that's why we call it 28. On the side facing the Earth, you have your full moon. So if the Earth is on the complete, is in between the sun and the moon, you're going to have a full moon. If the moon is between the sun and the earth, you're going to have a new moon because we cannot see the surface of the moon at that point in time. And based on that, your first quarter is when we have our most of what we see of our moon on the right, and your last quarter is what we're going to see on the left. Waning means that it is going towards the sun. Waxing means it is going away from the sun. So waxing, of course, appears to be larger. So as it's getting larger, even that is our first quarter. And then we have our full moon. Waning means it seems like it's getting smaller. So it is going towards the sun, away from the other side of the earth. So you'll see their third quarter, and eventually you get your new moon. So the word month is derived from the same root word for moon, and that's why we call it a month. So eclipses. Eclipses occur when the moon, sun, and earth are directly between one another. So it is either when the earth casts a shadow on the moon or when the moon casts a shadow on the earth. So the sun is being eclipsed is called a solar eclipse. That's being the moon is between the sun and the earth. The darkest portion of the moon shadow is called the umbra, and this happened in 2017 in August, and it actually happens again in 2024. So if you get a chance, you're lucky enough, if you live in the area, to have seen both of those in your lifetime. So what we see, the path of the moon. So it takes anywhere for an hour. And then it gradually gets lighter again. So it takes anywhere from 75 minutes to go into the shadow, to create a shadow, and then it takes somewhere around 75 minutes for it to come out. So we're looking at close to 3 hours for a solar eclipse. Now, a lunar eclipse is when the Earth is between the sun and the moon. So this means the moon is being completely covered up or eclipsed, calling it a lunar eclipse. And also the Latin name for our moon is Luna. Pretty cool looking, huh? To see how the Earth's umbra, or their shadow, moves into or moves across the moon's surface. All right, so the moon is made up of different particles, mostly the same particles of what we see on Earth. So many depressions on the moon were formed by meteorites, asteroids, comets that strike it. It does not have an atmosphere, and thus our very small, thin atmosphere. Thus, it is easy for asteroids to crater on it. So these depressions are called craters. Maria is a mountain or a dark-colored surface or lava-filled flat regions. So it is Latin for the word mountain, but these are actually going to be flatter regions of the moon's surface, meaning the ones that there are mountains because they're not cratered in, because they're much higher than the craters themselves. Thus, they're called Marias. Surrounding the large depressions filled with lava areas are thrown upwards in, and they form these mountains. So when you have that crater, it creates this mountain. So impacts on the moon throughout history led to the accumulation of the dusty lunar material called regolith. So basically moon dust. So the moon's interior is a lot like the Earth. It has a core, it has a mantle, but they are not free moving like the Earth's is. So the mantle is solid, dense iron, and it is iron-rich solid core. So here's the theory of how the moon came to be. So the moon formed about 4.6 billion years ago when a Mars-sized object, so a large body, collided with the Earth. So after colliding, the cores of the two bodies combined and settled towards the center of the larger object, thus pushing the debris out from this collision and forming it with the gases to create the moon. So gas and other debris were thrown into orbit, and gradually they turned into this solid mass. So as they're in this rotation around the Earth, they're forming the same way the Earth does as well. And that's the giant impact theory of how the moon came to be. Because an object so large would have to collide with the Earth and not just be thrown into its orbit. That's why we assume that it was pushed outward. All right. So, I know, long-winded, but that should cover the rest of your work for this unit.